We're going to take a look at problem solving as it applies to projectile motion. In many ways, it's very much what we've been doing, but it has some specific changes that we want to look at. Really, we want to look at a larger problem-solving strategy that will serve us as we go into more and more complex two-dimensional and eventually some three-dimensional problems. The big idea here is that you're going to analyze motion in both the x and the y direction separately, and then we're going to combine those results to have an answer about projectile motion. We have our x-axis constant velocity equations, and we have our y-axis constant acceleration equations, and we want to make sure we understand all these variables. When something is going in a trajectory like this, you might think about all the possible things that you could measure. And there are a lot of them, so it can get a little bit overwhelming if you're not paying a ton of attention. And so the first thing to do would sort of be to get a sense of if y up, or up is positive y and to the right is positive x, which of these variables are positive or negative? Well, there are some of them that are always the same, right? Like the acceleration in the y direction is always going to be down and negative. The acceleration in the x direction is always going to be 0. The position in the y and x direction will depend purely on where they are on the grid and what you've called the origin. And the velocity signs will depend on whether it is moving up, down, right, or left. All right, so if we look at the first position, number 1, right, we have a positive x position, a positive y position. It's moving up and to the right, so both velocity vectors are positive. The acceleration in the x always 0. The acceleration in the y always negative. If we look at position 2, right, we're still in the positive position in x and y. The velocity in the x is still positive, but the y velocity is 0 because we've reached the highest height. The x acceleration is 0, and the y acceleration continues to be negative. Moving on to position 3, right, we're still in the positive quadrant for position, but now the y velocity has changed direction, is now down, so negative. The acceleration in the x direction is 0. The acceleration in the y direction continues to be negative. Position 4 is interesting because we've now dropped down below the origin. This may be firing a cannon off of a cliff, kind of an example. And we have x is still positive, still to the right, but y is now negative, below where it started. Y velocity still negative, moving downward. X acceleration still 0, and y acceleration still negative. So once we've kind of gotten a sense of what all these variables can do, we also want to have a sense of what connects both the x and the y direction motion. There's only one variable, and highlighted in red here on the screen to make the point, is that time is the only thing that is the same for both, right? You cannot move horizontally well in projectile motion without also moving vertically. You have to move in both directions at the same time. So if you can find time using one set of equations, you know it for the other, and that is actually the key here. So the problem-solving strategies that we've developed and started to think about still apply. You still make a prediction. You still draw a sketch with origin in positive directions. We just have more variables. We write down our data, the things we know, we want, we're not given. We select appropriate equation or equations, isolate it symbolically, plug in data with units and signs, calculate, and then check our answer. So on page 43 in your packet, you will see this set of information, right? We're going to do some problem solving practices. We want to make sure that we're showing both the positive and negative x and y axes. And then there are a lot of variables here, right? Time, position, initial and final in both the x and the y, initial and final velocities in both the x and the y, total velocity at the beginning, angle, and little g. So there can be a lot to write down. You want to leave yourself plenty of room. So you're going to probably want a nice big blank piece of paper. When we're doing these, we, for simplicity, usually call the starting point time 0 and position 0. You don't have to, but this can help us all kind of talk about the problem together. And it's really helpful if we call up the positive y direction for this type of problem. So if the projectile is launched horizontally, that actually makes our lives very simple because The x and y position are 0, the angle is 0, the initial y velocity is 0, and the equations just simplify down to these, which we kind of looked at the beginning. X final equals vxt, and then just gt squared, 1/2 gt squared, and so on. If it's launched at an angle, you need to figure out what the x and y components are. You need to use your trig to do so. So now we get to our problem solving. We need to check our solution strategy. Usually, we first need to use information given to find time, which is what we're often not given, and then convert that in the other set of problems to the variable we actually want to solve for. So, movie stuntman problem is going to run across a rooftop horizontally, not jumping on a trampoline or anything to launch himself upward, and land on the roof of the building next door. Before the jump, we're checking to make sure it's safe based on the running speed of 4.5 meters per second. Can he make this jump? Well, our wanted variable is kind of unknown here. What do we want to know? Will he make it 6.2 meters? That's probably the thing we want to know. So it's not actually 6.2 meters, a delta x, or distance traveled. It's actually what is the final x position. So there's a couple ways to approach this, but usually when you draw your coordinate system and you think, well, we can figure out how far he falls, 4.8 meters, that's known. And if we figure out how long that takes, we should be able to figure out if he can make it across. So in the x-axis direction, what do we know? Well, we know that we want to know the final position. We know the initial and total constant velocity, but we're not given the time. So we need to find time in order to use this equation to get our final solution. And so we want to then look at what we have in the y direction. When we want time, we know the final y position, the initial y position being 0, and we know that the initial velocity in the y is 0 as well. So we can use an equation, y final equals 1/2 gt squared, to solve, plug in our values, and you end up with about a second, 0.98 seconds. Once we know that, we can go back to our x-axis, plug that in, and find that the stuntman will travel 4.4 meters, which is not far enough, right? That's less than the 6.2 they need to make the jump safely. We could also solve this kind of problem when things are launched at an angle. There's a little bit more to do here because we have to figure out components. In this case, we want to figure out how far away it lands. And we're first going to just do a quick estimate. If we've got a 30-degree angle, there's some things you probably already know. You've used trig a bunch. So you know that the x component and the y component of the velocities are going to come from the sine and cosine of 30. That's 50 meters per second in the y direction, which is good because that's an easy number to figure out how long it's in the air. This other number you may not have estimated perfectly, but most of you are better at that than I am. Time in the air is about 10 seconds, 5 seconds up, 5 seconds down. So we could say it lands somewhere between 800 and 900 meters away. This is an estimate after all. Now that we have this already estimated, it should be pretty easy to figure out the solution because we know that in the x direction, we have a velocity. We know we want to know the final position. We're not given time. Similarly to the last problem, we want to find that time variable in the y direction. There's lots there that we can look at, right? We know the initial and final y positions are both 0. We know that the initial y velocity is 50 meters per second, and we know little g. We're going to use one of our equations and solve that it takes about 10 or 10.2 seconds. We then go back, plug that in, and find out that the projectile travels about 890 meters. So that's kind of it for the examples. I'm going to leave you this problem. A projectile fired off a cliff at 25 meters per second at an angle of 30 degrees below the horizontal lands 48 meters from the cliff base. How high is the cliff? So this is an x position question. The first step you're going to want to do is find the components of that initial velocity. And The little sticky note note there says, try it and submit the solution to Classroom. So that's going to be the evidence that you've read through this and figured out how to do it. It does not have to be a perfect solution. I'm not grading it, but I would like to see you try to set up a problem to kind of get a look at your thinking. I'll see you in class.